Welcome to week 3. This week is focused on question answering, which allows you to build a system that could respond to questions. You can build a model that answers questions by generating text or by finding text in an existing paragraph. This week we will be using the BERT model. BERT stands for the bidirectional encoder representations from transformer. You will also see how you can use the Hugging Face platform to find existing models and use them. In the real world, it is often the case that you will not be building the models from scratch, so we will also show you how to use existing models. Jonas will show you the details.
Yes, let's see how this works. Good to see you again. In this week, you will learn about transfer learning, which is a new concept in this course. Transfer learning allows you to get better results and speeds up training. You'll also be looking at question answering. So let's dive in.
So in week 3 of course 4, you're going to cover many different applications of NLP. And one thing you're going to look at is question answering. So given a question and some context, can you tell us what the answer is going to be inside that context? Another thing you're going to cover is transfer learning. For example, knowing some information by training something in a specific task. How can you make use of that information and apply it to a different task? You're going to look at BERT, which is known as the bidirectional encoder representation, which makes use of transformers. And you'll see how you can use bidirectionality to improve performance. And then you're going to look at the T5 model. And basically what this model does, you can see here, it has several possible inputs. So it could be a question, you get an answer. It could be a review and you'll get the rating over here. And it's all being fed into one model. So let's look at question answering. And over here you have context-based question answering, meaning you take in a question and a context, and it tells you where the answer is inside that context over here. So this is the highlighted stuff, which is the answer. And then you have closed book question answering, which only takes the question and it returns the answer without having access to a context. So it comes up with its own answer. So previously, we've seen how innovations in model architecture improved performance, and we've also seen how data preparation could help. But over here, you're going to see that innovations in the way the training is being done also improves performance, in which case you'll see how transfer learning will improve performance. So this is the classical training that you're used to seeing. You have a course review. This goes through a model, and let's say you predict the rating, and then you just predict the rating the same way as you've always been doing. So nothing changed here. This is just an overview of the classical training that you're used to. Now, in transfer learning, let's look at this example. Let's say that you have movie reviews, and then you feed them into your model and you predict a rating. And over here, you have the pre-trained task, which is on movie reviews. Now, when training, you're going to take the existing model for movie reviews, and then you're going to fine tune it or train it again on course reviews, and you'll predict the rating for that review. So as you can see over here, instead of initializing the weights from scratch, you start with the weights that you got from the movie reviews, and you use them as a starter point when training for the course reviews. And at the end, you do some inference over here, and you do the inference the same way you're used to doing. You just take the course review, you feed it into your model, and you get your prediction. So you can also use transfer learning on different tasks. This is another example where you feed in the ratings and some review, and this gives you sentiment classification. And then you can train it on a downstream task like question answering, where you take the initial weights over here and you train it on question answering. So when is Pi Day? And the model answers March 14th. And then you can ask the model the same question, when's my birthday over here? And it does not know the answer. But this is just another example of how you can use transfer learning on different tasks. So now we're going to look at BERT, which makes use of bidirectional context. So in this case, you have learning from deep learning AI is like watching the sunset with my best friend. And over here, the context is everything that comes before. And then let's say you're trying to predict the next word, deep learning AI. Now, when doing bidirectional representations, you'll be looking at the context from this side and from this side to predict the middle word. And this is one of the main takeaways for bidirectionality. So now let's look at single task versus multitask. Over here, you have a single model, which takes in a review and then predicts a rating. And over here, you have another model, which takes in a question and predicts an answer. So this is a single task each, like one model per task. Now, what you can do here with T5 is it is the same model that's being used to take the review, predict the rating, and then take the question and predict the answer. So instead of having two independent models, you end up having one model. So let's look at T5. And over here, the main takeaway is that the more data you have, generally the better performance there is. So for example, the English Wikipedia dataset is around 13 gigabytes compared to the C4 colossal cleaned crawled corpus is about 800 gigabytes, which is what T5 was trained on. And this is just to give you like how much larger the C4 dataset is when compared to the English Wikipedia. So what are the desirable goals for transfer learning? First of all, you want to reduce training time because you already have a pre-trained model. So hopefully, once you use transfer learning, you'll get faster convergence. It will also improve predictions because you learn a few things from different tasks that might be helpful and useful for your current predictions on the task you're training on. And finally, you might require or need less data because your model has already learned a lot from other tasks. So if you have a smaller data set, then transfer learning might help you.
You now know what you're about to learn. I am very excited to show you all these new concepts. In the next video, we will start by exploring transfer learning. This week, I'll be talking about transfer learning with the full transformer. I'll also talk a little bit about BERT, which is the bidirectional encoder representation for transformers. Then, I'll talk about a special model known as the T5 model, which you'll learn about. Now, all of these concepts make use of transfer learning. So what is transfer learning? Let me show you.
You'll now take a look at the transfer learning options that you'll have while performing your NLP tasks. So this is a quick recap where you have your train data, goes into a model, then you have a prediction. So transfer learning will come in two basic forms. The first one is using feature-based learning, and the other one is using fine-tuning. And by feature-based, I mean things like word vectors being learned. And fine-tuning is you take an existing model, existing weights, and then you tweak them a little bit to make sure that they work on the specific task you're working on. So there is pre-trained data, which makes use of labeled and unlabeled data. Let's say you're training your model on sentiments for product reviews, and then you can use those same weights to train your model on course reviews. And then the other thing is pre-training task, which usually makes use of language modeling. For example, you mask a word and you try to predict what that word is, or you try to predict what the next sentence would be. So let's look at general purpose learning, and this is something that you're already familiar with. So over here you have I am because I'm learning, and you're trying to predict the central word. So the central word is happy over here. And you used a model known as the continuous bag of words model, or at least you got the following embeddings. So now you can use these embeddings as the input features in translation tasks to translate from English to German. So let's look at a more concrete example of feature-based versus fine-tuning. So over here you have word embeddings, you put it in your model, you get a prediction. And then over here, you get some type of new features or new word embeddings. And then you feed them into a completely different model. And this gives you your prediction. Now, on the fine-tuning side, you have your embeddings. You feed it into your model, you get a prediction. And then you fine-tune on this model, so on a downstream task. And then you have some new inputs on your new weights that you fine-tuned, so you feed it in, and you get a prediction. So let's look at fine-tuning. This is a way to add fine-tuning to your model. So let's say you have movies and you're predicting 1 star, 2 stars, or 3 stars. So you pre-trained, and let's say now you have course reviews. So one way you can do this is you fix all of these weights that you already have, and then you add a new feed-forward network while keeping everything else frozen here. And then you just tune on this new network that you just added. Data affects performance a lot. So in this case, you have data being fed into your model and you get some neutral outcome. But as you have more data and you build a larger model over here, then you get a much better outcome. So the more data you have, the better it is. And the more data you have, the bigger the models you can build will be able to capture the task you're trying to predict on. So let's look at labeled versus unlabeled data. Now, this is just a graphic example that tells you that usually you'll have way more unlabeled text data than labeled text data. And here's an example. So in pre-training, you have no labels. You feed this into your model. And then in downstream task, you could have something like what day is Pi Day. You feed it into your model and you get the March 14th. So, and remember, these are the word vectors we're talking about. So which tasks work with unlabeled data? This is a self-supervised task. So you have the unlabeled data, and then you create input features, you create targets or labels, and this is how it works. So you have unlabeled data. Learning from deep learning AI is like watching the sunset with my best friend. You create the input and then blank. So the sunset with my best blank. So you're trying to predict friend. So you feed this into your model, you get your prediction. So the target is friend, your prediction goes in, you have the loss here, and then you use this loss to update your model. And this is basic language modeling that you've already seen before. So let's look at fine-tuning a model in the downstream task. So you have your model here. You did some pre-training on it, either by masking words or predicting the next sentence. And then you use this model to train it on downstream tasks. So you can use this model, fine-tune it on translation or summarization or question answering. So here's a summary of what you've seen so far. Usually you have some trained data, you have a model, you make a prediction. We use transfer learning to get feature-based examples or fine-tuning. So feature-based like word vectors or word embeddings, and fine-tuning is something that you can do on downstream tasks. And then we can also use labeled data and unlabeled data to help us. So you can train something on a different task on a different data set, and that will also help a little bit. And then you can use pre-training tasks like language modeling or masked words or next sentence prediction.
You have now seen some advantages of transfer learning. I'll show you a chronological order of when the models were discovered. We will also see the advantages and the disadvantages of each model. Let's start.
So this is a quick outline where you can see we start here with continuous bag of words model, then we got Elmo, then we got GPT, then we got BERT, and finally we ended up having T5 and so more. Like over here, you're going to end up having many more models coming up, hopefully soon. So this is not a complete history of all relevant models and research findings, but it's useful to see what problems arise with each problem and what problems each method solves. So let's look at context over here. Let's say we have the word right, and ideally we want to see what this word means. So we can look at the context before it, and then we can also look at the context after it. And that's how we've been able to train word embeddings so far. So the continuous bag of words, over here you have the word right. And previously what you've been doing, you would take a fixed window, say 2 before and 2 after, or 3 or 4, whatever C is for the window size. And then you will take the corresponding words, feed them into a neural network, and predict the central word in this case, which is right. Now, the issue over here is that what if we wanted to look at not only the fixed window, but all the words before and all the words after? And how can we do that? So if we want more context, let's say we want they were on D, over here, this is like the first left part of the sentence, and then all the right parts of the sentence. So instead of having the fixed window, we want to add like the street or history, for example. So to use all of the context words, what researchers have done, they explored the following using RNN. So they would use an RNN from the right and from the left, and then they would have a bidirectional LSTM, which is a version of a recurrent neural network. So you feed both of them in, and then you can predict the center word right. So that gives you the word embedding for the word right. Now, OpenAI GPT, what it did, so we had transformer, so the encoder decoder architecture that you're familiar with. And then we ended up having this GPT, which makes use of a decoder of stacks only. So in this case, we only have one decoder, but you can have several decoders in the picture. Elmo made use of RNNs or LSTMs, and we would use these models to predict the central word. So the thing with Elmo is that you only looked at one direction. You could not look at the remaining parts of the sentence from the right side. So why not use a bidirectional model? So in this case, this is the transformer, and you can see that in the transformer over here, each word can peek at itself. So if we were to use it for on the right, you can only look at itself. But the issue is that you cannot peek forward. And remember, you've seen this in causal attention, where you don't look forward, you only look at the previous ones. So BERT came and helped us solve this problem. So this is a recap. Transformers encoder decoder, GPT makes use of decoders, and BERT makes use of encoders. So over here you have the legislature believed that they were on the blank side of history, so they changed the law. And over here we can make use of bidirectional encoder representation from transformers, and this will help us solve this issue. So this is an example of a transformer plus bidirectional context. So you feed this into your model, and then you get right and of. Because of this, you're able to look at the sentence from the beginning and from the end and make use of the context to predict the corresponding words. So if we're to look at words to sentences, meaning instead of trying to predict just the word, we'll try to predict what the next sentence is. So given the sentence over here, the legislators believed that they were on the right side of history. Is this the next sentence or is this the next sentence? So you have a sentence A, and then you try to predict the next sentence, sentence B. So in this case, it's obviously, so they changed the law. So BERT pre-training tasks makes use of multi-mask language modeling. So the same thing that you've seen before, and it makes use of next sentence prediction. So it takes two sentences and it predicts whether it's a yes, meaning sentence 2 follows sentence 1, or sentence B follows sentence A, or not. So let's look at encoder versus encoder decoder. So over here you have the transformer, which had the encoder and the decoder stack. And then you had GPT, which just had decoder stack. And then BERT, just the encoder stack. So T5 tested the performance when using the encoder decoder, as in the original transformer model. And the researchers found that the model performed better when it contained both the encoder and the decoder stacks. So let's look at the multi-task training strategy over here. So you have studying with deep learning.ai it's being fed into the model and it gives you a 5-star rating. And hopefully it's a 5-star rating. And then you have a question and then you get the answer. But the question here is, how do you make sure that the model knows which task it's performing in? Because you can feed in a review over here. And how do you know that it's not going to return an answer instead? How do you know it's going to return a rating? Or if you feed in a question, how do you know it's not going to return some, numerical output or some text version of a numerical output? So let's see how to do this. Over here is an example where, let's say you're trying to classify whether this is 5 stars or 4 stars or 3 stars. So you append the string classify, for example, and then it classifies it and you get 5 stars. Let's say you want to summarize. So you add the string summarize colon. It goes into the model. It automatically identifies that you're trying to summarize, and it says that it was all right. You have a question, you append the question string, it knows that it's a question, and it returns the answer. Now, these might not be the exact tags that you'll find in the paper, but it gives you the overall sense of the idea. So in summary, you've seen the continuous bag of words model, which makes use of a fixed context window. You've seen Elmo, which makes use of a bidirectional LSTM. You've seen GPT, which is just a decoder stack, and you can see kind of unidirectional in context. Then you've seen BERT, which makes use of bidirectional encoder representation from the transformer, and it also makes use of multi-mask language modeling and next sentence prediction. And then you've seen the T5, which makes use of the encoder decoder stack and also makes use of mask and multitask training.
You have now seen an overview of the models. You have seen how the text-to-text model has a prefix. With the same model, you can solve several tasks. In the next video, we will be looking at the BERT model in more detail, also known as the bidirectional encoder representation for transformers. I'll now teach you about bidirectional encoder representations for transformers, or in short, just BERT. BERT is a model that makes use of the transformer, but it looks at the input from two directions. Let's dive in and see how this works.
Today you're going to learn about the BERT architecture, and then you're going to understand how BERT pre-training works and see what the inputs are and the outputs are. So what is BERT? BERT is the bidirectional encoder representation from transformers, and it makes use of transfer learning and pre-training. So how does this work? Usually starts with some input embedding, so E1, E2, all the way to some random number En. And then you go through some transformer blocks, as you can see here. So each blue circle is a transformer block, goes up furthermore, furthermore, and then you get your T1, T2, Tn. So basically there are two steps in BERT framework, pre-training and fine-tuning. And during pre-training, the model is trained on unlabeled data over different pre-training tasks, as you've already seen before. And for fine-tuning, the BERT model is first initialized with the pre-trained parameters, and all of the parameters are fine-tuned using labeled data from the downstream tasks. For example, in the figure over here, you get the corresponding embeddings, you run this through a few transformer blocks, and then you make the prediction. So we'll discuss some notation over here. So first of all, BERT is a multi-layer bidirectional transformer. It makes use of positional embeddings. And the famous model is BERT base, which has 12 layers or 12 transformer blocks, 12 attention heads, and 110 million parameters. And these new models that are coming out now, like GPT-3 and so forth, they have way more parameters and way more blocks and layers. So let's talk about pre-training. So before feeding the word sequences to the BERT model, we mask 15% of the words. And then the training data generator chooses 15% of these positions at random for prediction. And then if the ith token is chosen, we replace the ith token with 1, the mask token, 80% of the time. And then 2, a random token 10% of the time. And then 3, the unchanged ith token 10% of the time. So in this case, then Ti, what you've seen in the previous slide, will be used to predict the original token with cross entropy loss. So in this case, this is known as the masked language model. And over here we have after school, Lucas does his blank in the library. So maybe work, maybe homework, one of these words that your BERT model is going to try to predict. And to do so, usually what you do, you just add a dense layer after the Ti token and use it to classify after the encoder output. So you just multiply the output vectors by the embedding matrix, and then to transform them into vocabulary dimension, and you add a softmax at the end. So this is another sentence after school, Lucas does his homework in the library. And then after school, blank, his homework in the blank. So you have to predict Lucas does and then library also. So in summary, you choose 15% of the tokens at random. You mask them 80% of the time, replace them with a random token 10% of the time, or keep as is 10% of the time. And then note that there could be multiple masked spans in a sentence, so you could mask several words in a same sentence. And in BERT, also next sentence prediction is also used when pre-training. So given two sentences, if it's true, it means the two sentences follow one another, otherwise they're different. They don't lie in the same sequence in the text.
You have now developed an intuition for this model. You have seen that BERT makes use of next sentence prediction and masked language modeling. This allows the model to have a general sense of the language. In the next video, I'm going to formalize this and show you the loss function for BERT. Please go on to the next video. I will be talking about the BERT objective. You'll see what you are trying to minimize. Specifically, I'll show you how you can combine word embeddings, sentence embeddings, and positional embeddings as inputs. Let's take a look at how you can do this.
So you're going to learn how BERT inputs are fed into the model and the different types of inputs and their structures. Then you're going to visualize the outputs. And finally, you're going to learn about the BERT objective. So formalizing the input, this is the BERT input representation. So you start with positional embedding. So they allow you to indicate the position in the sentence of the word. So where each word is in the corresponding sentence. So you have this. Then you have the segment embeddings, and they allow you to indicate whether it is sentence A or sentence B. Because remember, in BERT, you also use next sentence prediction. And then you have the token embeddings or the input embeddings. And you also have a CLS token, which is used to indicate the beginning of the sentence, and a SEP token, which is used to indicate the end of the sentence. And then what you do, you just take the sum of the token embeddings, the segmentation embeddings, and the position embeddings, and then you get your new inputs. So over here, you can see you have masked sentence A, you have masked sentence B, they go into tokens, and then you have the CLS token, which is a special classification symbol added in front of every input. Then you have the SEP token, which is the special separator token. You convert them into the embeddings, so then you get your transformer blocks. And then you can see at the end, you get your T1 to Tn, your T1 prime to Tn prime. So these are each Ti embedding will be used to predict the masked word via a simple softmax. And you have this C also embedding, which can be used for next sentence prediction. So let's look at the BERT objective now. So for the multi-mask language model, use a cross-entropy loss to predict the word that's being masked or the words that are being masked. And then you add this to a binary loss for the next sentence prediction. So given the two sentences, do they follow one another or not? So in summary, you've seen the BERT objective and you've seen the model inputs and outputs.
In the next video, I will show you how you can fine-tune this pre-trained model. Specifically, I'll show you how you can use it to your own tasks for your own projects. Please go on to the next video. Using BERT can get you state-of-the-art results on many tasks or problems. In this video, I'm going to show you how you can fine-tune this model so that you can get it to work on your own datasets. Let's take a look at how you can do this.
So right now you're going to see how you fine-tune BERT. So during pre-training, remember you had sentence A and sentence B, and then you used next sentence prediction and you used masked tokens to predict the masked tokens that you masked from each sentence. So that's in pre-training. Now, if you want to go on to MNLI or like hypothesis premise scenario, then instead of having sentence A and sentence B, you're going to feed in the hypothesis over here and the premise over here. For NER, you're going to feed in the sentence A over here, and then the corresponding tags over here. For question answering, you'll have squad, for example, you'll have your question over here, and then your answer over here. So visually, what does this look like? So remember this image from the BERT paper. So this is what ends up happening. Over here, you have the question. Over here, you'll have the paragraph, and this will give you like your answer, the start and the end of the answer. Then for NER, again, you'll have the sentence and the corresponding named entities. For MNLI, you'll have the hypothesis and then the premise, and so forth. So in summary, given the place of sentence A and sentence B, you can fill it with a text in part for sentence A, and then say like a null symbol to say that you're trying to classify the text, whether it's for sentiment analysis, like happy or sad. So that's one way to do it. Question passage for question answering. You could have hypothesis premise for MNLI. You could have sentence with the named entities for NER. You can have a sentence and a paraphrase of the sentence. You could have an article and a summary, and so forth. So this is just the inputs into your BERT model.
Now that you know how to fine-tune your model on classification tasks, question answering, summarization, and many more things, we'll take it to the next level and introduce you to a new model known as the T5. Please go on to the next video to learn about the T5 model. The T5 model could be used on several NLP tasks, and it also uses similar training strategy to BERT. Concretely, it makes use of transfer learning and masked language modeling. The T5 model also uses transformers when training. So let's take a look at how you can use this model in your own applications.
So you're going to understand how T5 works. Then you're going to recognize the different types of attention used and see an overview of the model architecture. So T5 transformer is known as the text-to-text transformer, and you can use it in classification. You can use it for question answering to answer a question. You can use it for machine translation. You can use it for summarization, and you can use it for sentiment. And there are other applications that you can use T5 for, but we'll focus on these for now. So the model architecture and the way the pre-training is done, first of all, is you have an original text, something like this, where you have, "Thank you for inviting me to your party last week." So you mask the certain words, so for inviting me last, and then you replace it with these tokens like bracket X, bracket Y. So bracket X corresponding to for inviting, and bracket Y corresponding to last. And your targets are going to be bracket X for inviting, bracket Y last. And these tokens or these brackets, like they keep going in increment order. So then it's bracket Z, then maybe bracket A, bracket B, and so forth. So each bracket corresponds to a certain target. The model architecture and the different transformer architecture variants that we're going to consider for the attention part here. So we start with the basic encoder decoder representation. So you can see over here you have fully visible attention in the encoder, and then causal attention in the decoder, and then you have the general encoder decoder representation. Just as a notation, so light gray lines correspond to causal masking and dark gray lines correspond to the fully visible masking. So on the left, as I said again, it's the standard encoder decoder architecture. In the middle over here, what we have the language model, which consists of a single transformer layer stack, and it's being fed the concatenation of the inputs and the target. So it uses causal masking throughout, as you can see, because they're all gray lines. And you have x1 going inside over here, get its x2, x2 goes into the model, x3, and so forth. Now, over here to the right, we have prefix language model, which corresponds to allowing fully visible masking over the inputs, as you can see here in the dark arrows, and then causal masking in the rest. So as you can see over here, it's doing causal masking. So the model architecture, it uses encoder decoder stack. It has 12 transformer blocks each. So you can think of it as a dozen eggs, and then 220 million parameters. So in summary, you've seen prefix language model attention, you've seen the model architecture for T5, and you've seen how the pre-training is done similar to BERT, but we just use masked language modeling here.
You now have an overview of the transformer model. You know how to train it, and you've seen that you can use it on multiple tasks. In the next video, I'll be talking about a few training strategies for this model. See you there! Welcome! You will now see how you can train one model to get you very good results on several NLP tasks. When training such a model, we usually append a tag to notify whether we're training on either machine translation, question answering, summarization, sentiment, or some other type of task. Let's see how you can use this in your own applications.
So the multitask training strategy works as follows. So if you want to translate from English to German, you append the prefix translates English to German, and it gives you the corresponding translation. For cola sentence, like the course is jumping well, and it says it's not acceptable because it's grammatically incorrect. If you have two sentences and you want to identify their similarity, you put in the STSP sentence 1 and then sentence 2 inside over here. Sentence 1, sentence 2, and then you get the corresponding score. If you want to summarize, you add the summarize prefix to the article or the text you want to summarize, and it gives you the summary. So this is how it works. Inputs and outputs format. So for machine translation, you just do translate like blank to blank, and you add the sentence. To predict entailments, contradiction, or whether it's neutral, you would feed in something as follows. So MNLI premise, I hate pigeons, then the hypothesis, my feelings towards pigeons are filled with animosity, and the target is entailment. So basically over here, this is gonna try to learn the overall structure of entailment. And by feeding in the entire thing, the model would have full visibility over the entire input, and then it would be tasked with marking a classification by outputting the word entailment. So it is easy for the model to learn to predict one of the correct class labels given the task prefix, MNLI in this case. If you know the main difference between prefix LM and the BERT architecture is that the classifier is integrated to the output layer of the transformer decoder in the prefix LM. And over here you have the Winograd schema, which is another way to predict whether a pronoun, for example over here, the city councilman refused the demonstrators a permit because they feared violence. So you're going to feed this into your model, and then it will be tasked to predict they as the city councilman. So for multitask training strategy, this is a table found in the original paper, and we'll talk about what the glue benchmark is, and these other benchmarks, you can check them out. But for the purpose of this week, we'll be focusing on the glue benchmark, which would be the next video. And we'll talk about adapter layers and gradual unfreezing. But these are the scores reported. And you can see that the T5 paper actually reaches state of the art in many tasks. So how much data from each task to train on? So for the data training strategies, there is examples proportional mixing. And in this case, what you end up doing, you take an equal proportion, say like 10% from each data that you have. And if the first data set, for example, blue, you take 10% of this, then you'll get 10% over here. 10% of this is larger. And 10% is just a random number I picked, but you get the point. For the other type of data training strategy is equal mixing. So regardless of the size of each data, you take an equal sample. And then there's something in the middle called temperature scaled mixing, where you try to play with the parameters to get something in between. Now we'll talk about gradual unfreezing versus adapter layers. So in gradual unfreezing, what ends up happening, you unfreeze one layer at a time. So you say this is your neural network, unfreezing the last one, you fine tune using that, you keep the others fixed, then unfreezing this one, and then you unfreeze this one. So you keep unfreezing each layer. And for the adapter layers, you basically add a neural network to each feed forward in each block of the transformer. And then these new feed forward networks, they're designed so that the output dimension matches the input. And this allows them to be inserted without having any structural change. When fine-tuning, only these new adapter layers and the layer normalization parameters are being updated. So we'll talk now a bit more about fine-tuning. The approach that's usually being used here has the goal of training a single model that can simultaneously perform many tasks at once. For example, the model, most of its parameters are shared across all of the tasks. And we might train a single model on many tasks, but when reporting performance, we can select a different checkpoint for each task. So over here, the task could be like translation, summarization, or masked language modeling. And they do the training.
You learned about the
to
multiple
power
training
of
strategies used for your transformer model. In this week's programming exercise, you'll explore this in even more detail. Now that you know how to train this model, you need the way to evaluate it. Concretely, you'll be evaluating it using the GLUE benchmark, which stands for General Language Understanding Evaluation Benchmark. See you there! I will show you one of the most commonly used benchmarks in natural language processing. Specifically, you'll learn about the GLUE benchmark. This is used to train, evaluate, analyze NLP tasks. Let's take a look at this in some more detail.
So the GLUE benchmark stands for General Language Understanding Evaluation, and it is basically a collection that is used to train, evaluate, analyze natural language understanding systems. It has a lot of data sets, and each data set has several genres, and they're of different sizes and different difficulties. Some of them are, for example, used for coreference resolution. Others are just used for simple sentiment analysis. Others are used for question answering, and so forth. And it is used with a leaderboard, so people can use the data sets and see how well their models perform compared to others. So the tasks evaluated on could be, for example, sentence grammatical or not. For example, if a sentence makes sense or it does not. It could be used on sentiment. It could be used to paraphrase some text. It could be used on similarity, on question duplicates, whether a question is answerable or not, whether it's a contradiction, whether it's entailment, and also for the Winograd schema, which is basically trying to identify whether a pronoun refers to a certain noun or to another noun. So it's used to drive research. As I said, that researchers usually use the GLUE as a benchmark. It is also model agnostic, so it doesn't matter which model you use. Just evaluate on GLUE and see how well your model performs. And finally, it allows you to make use of transfer learning because you have access to several data sets and you can learn certain things from different data sets that will help you evaluate on a completely new data set within GLUE.
You now know not only how to implement state-of-the-art models, but you also know how to evaluate them. In the next video, I'll be talking about question answering, and I'll show you how you can use these models to build a sophisticated QA system. I'll see you there. Welcome to the last video of this week. You now see the fruits of your labor come together. In this video, I will walk you through how you can build a QA system. Question answering is a really cool application, and you can use it in almost any application you are building. So let's dive in and see how you can do this.
So previously you've seen the transformer decoder, and now you're going to look at the transformer encoder. So it's very similar. You have the input embeddings that are going in, then you have positional encoding, you have multi-attention head, add and normalization, then a feed forward, then another add and normalization. And then this goes into the decoder architecture. So right now we'll be looking at the feed forward. So you have a layer norm, a dense, followed by an activation. Then we have a dropout in the middle, followed by a dense layer, and then a dropout final. So this is what you'll be implementing in this week's programming assignment. Then you have the encoder block. So the encoder block has a layer norm, has the attention, then the dropout. And then it has another residual connection within a feed forward. So this is the code for this image over here. So putting them together, you have the feed forward here. And then you have the encoder block, which has the feed forward and two residual connections. So the first one and the second one here. Now, the other thing you'll be looking at in this week's programming assignment is the data sets. So you'll have a question like this, like what percentage of the French population today is non-European? You'll have a context, and then you'll have a target. So the answer is approximately 5%, which could be found here. So here's exactly what you'll be doing. You'll be loading in a pre-trained model, and then you're going to process your data set such that you'll have question, followed by the question, context, followed by the context as input, and A as target for answer. Then you will fine-tune your model on the new task and inputs, and then you'll predict using your own model. And remember, this is the T5 that you'll be working with.
You have learned about the multiple training strategies used for the T5 model. In this week's programming assignment, you'll get to explore this route in even more detail.
Hi, I'm Lysander from the open source team at Hugging Face. At Hugging Face, we specialize in democratizing machine learning. We want to make machine learning as accessible as possible, and we firmly believe the only way to do so is through open source and open science. We develop and create tools centered on the machine learning community. Tools like the Transformers library, which supports dozens of transformer architectures that can be easily used in any natural language processing, computer vision, or speech project. Tools like the datasets library, to easily download and pre-process more than 1,000 different datasets. And tools like Accelerate, tokenizers, and others to simplify machine learning from data handling to modeling, training, and post-processing. These tools make up the Hugging Face ecosystem, an ecosystem connected by the Hugging Face Hub, a platform to collaborate on machine learning models and datasets. Before you get started with this lab by deeplearning.ai, let me introduce you to the Hub, which you will leverage in the next videos. The Model Hub is host to more than 15,000 community-contributed models. And it offers a way to select a model according to a task, a library, trained on a specific dataset, on a specific language, with a given license. Models can be from the Hugging Face Transformers library, but they're not limited to it. Any library can easily add hub support, and some, like SpaceC or AllenNLP among others, already do. Furthermore, we offer tools to push your own model and weights, with no requirement on the library. Models can be further described by their model cards, and other members of the community may play with the model using the hosted inference API. The Dataset Hub is similar to the Model Hub, hosting thousands of datasets, here too mostly community contributed. These datasets can then be selected by task, language, number of examples, and licenses. These datasets offer a comprehensive dataset card explaining how the dataset was designed, where the data came from, and considerations when using the data, both in terms of social impact and biases. Additionally, it offers a quick link to models fine-tuned or trained on these datasets. We're very excited to partner with deeplearning.ai on this course focused on transformers. In the upcoming labs, you'll get a chance to practice using some of the Hugging Face tools, like transformers, datasets, and the Hugging Face Hub, to fine-tune a pre-trained model. Have fun, and looking forward to seeing your fine-tuned models.
In this video, I'll introduce you to Hugging Face. I'll show you what it can provide you and how you can use it for your projects. Hugging Face is very well documented, and they even have a course on their website that I recommend you check out if you want to dig deeper into their ecosystem. Hugging Face offers a wide range of solutions for organizations, builds community, and has tools for collaborative research. However, I'll be focusing on their Transformers Python library, which is a great tool for using transformer models in your projects. You can use Hugging Face Transformers library alongside PyTorch, TensorFlow, or Flax, so you can leverage everything that Hugging Face has to offer without the need to change your favorite framework. There is also a growing support for Flax, which is a neural network library and ecosystem based on JAX. You can use Hugging Face Transformers library for basically two things. You can use it applying state-of-the-art transformer models for a variety of NLP tasks, and two, fine-tuning pre-trained models using your datasets or the ones provided by Hugging Face. The Transformers library has the pipeline object that encapsulates everything you need to run a model on your examples. With pipelines, you can easily use state-of-the-art transformer models right out of the box for different NLP tasks. I'll go through pipelines in more detail in later video, but let's go through a very general overview of what they do. Pipelines take care of pre-processing your inputs, running the model, and post-processing the outputs for you. So you have to provide the appropriate inputs for your task to get a human-readable result. Moreover, if you don't know what model to use for your task, you don't have to worry. Every pipeline has a default model. For instance, with a pipeline for question answering task, you can use a transformer to answer different questions provided a context. You only need to specify the pipeline's task and provide a context with the questions you want to ask. The pipeline takes care of everything else and gives you human-readable answers. So you can use transformer models for virtually any NLP task with Hugging Face pipelines. And if you want to fine-tune a pre-trained model, the Transformers library provides you different tools to do so, and without any complications, of course. Hugging Face has a growing library with more than 15,000 pre-trained model checkpoints that you can use to fine-tune the most popular transformer architectures. A checkpoint for any given model is just the set of parameters learned for a specific model that was trained with a particular data set for some task, like question answering. You can fine-tune a model from a starting checkpoint using one of the 1,000 data sets available as Hugging Face or with your own data. The Transformers library offers tokenizers associated with every checkpoint to pre-process the data. The tokenizers do the heavy lifting for you by translating your text to readable inputs for the model you want to fine-tune. If you use PyTorch, you can use the trainer included in the Transformers library or create a custom one to train the model. For TensorFlow, it is recommended to use traditional Keras methods like fits. Hugging Face also provides metrics like glue that seamlessly integrates into the training process to evaluate your model. And when you have a fine-tuned model, you can run it to get an output that tokenizers can help you transform into human-readable text. So Hugging Face and the Transformers library give you everything you need to fine-tune a transformer. However, you can customize any of the steps. Let's do a quick recap. The Transformers library has a pipeline object that you can use to apply state-of-the-art transformer models for different NLP tasks. Pipelines take care of pre-processing your inputs, running the model, and post-processing the outputs for you so it is human-readable. For instance, with a pipeline for the question answering task, you can use a transformer to answer different questions provided a context. To use a transformer model, you only need to indicate the task that you need your pipeline to work on. In other words, pipelines are objects that you build for specific NLP tasks. To initialize a pipeline, you only need to pass the task, but if you need, you can also indicate the model checkpoints you want to use. To use an initialized pipeline, you only need to provide the appropriate inputs that your task requires. Hugging Face supports the most popular NLP tasks, but Hugging Face does not focus only on NLP. It also supports other tasks such as image classification, object detection for computer vision, automatic speech recognition, and others. For instance, you could use the familiar sentiment analysis task if your goal is to classify a sequence as positive or negative. The input of this pipeline is a sentence, and the output is the category to which the sentence belongs. You can also create a pipeline for question answering. If you want a model that answers questions, extracting information from a context you provide. The input here is the context and a set of questions, and the model outputs the corresponding answers if it finds any. Another task that you might find helpful is fill mask, which you can use when you need your model to fill blank spaces in a text. This pipeline needs the sentence you want to fill and the exact position you need your model to fill it. It outputs a series of possible ways to complete the sentence. And there are many more tasks that you can find directly on the Hugging Face website. As I already told you, you can pick the specific model checkpoint that you want to use with your pipeline. Hugging Face provides a huge number of checkpoints, and some of them are fine-tuned using massive data sets to give exceptional results on specific tasks. However, it's best to keep in mind that not every checkpoint is suitable for every task, so you should check the description of the pre-trained models to select the appropriate checkpoint or stick with the defaults used by the pipeline. Finally, you could be asking, where can I find the proper model for my task and use the checkpoints? For that, Hugging Face has a model hub available at huggingface.com. There, you will find several pre-trained models. You will be able to filter by your desired task or even by the dataset or framework you need to use. Once you select the model that fits better to your needs, you will see the model card interface. The model card shows you information about your selected model, such as description of the same and some code snippets, such as a description of the same model and some code snippets with examples on how to use the selected model. Hugging Face provides you everything that you need to fine-tune a transformer model. They provide more than 1,000 datasets for specific tasks that you can quickly load using the datasets library. They also provide you with tokenizers that help you pre-process your data before the training and post-process the outputs after running the model. And they have more than 15,000 model checkpoints that you can load from the Transformers library. Additionally, the trainer object lets you train your model without worrying about coding the training procedure. And as if it wasn't enough, it also has predefined metrics that you can use to evaluate your model's performance, which can integrate into the trainer object. Hugging Face has more than 15,000 model checkpoints that you can use as starting points for your fine-tuning process. Recall that a model checkpoint is the set of weights learned for a model during a training procedure using a determined dataset. For instance, you could use a model checkpoint for the distilled version of the BERT transformer obtained by training on a question-answering dataset, which you can find as distill-base-case distill-squad in Hugging Face. Or, you could use the base version of the BERT model trained on a cased English corpus, which you can find as BERT-base-cased. So you can explore the Hugging Face model library to look for a checkpoint that you can use for your specific use case. Once you have selected the checkpoints you want to use, you can upload its architecture and weights using a single line of code using functions from the Transformers library. You'll see how to do that in the next ungraded lab, so don't worry about the code just yet. Now, to fine-tune a transformer model for a specific task or perform well in a particular domain, you need lots of data. You could get and process your datasets by scraping the web or even collecting data from an app you made. But Hugging Face has a library with task-specific datasets that is worth exploring before you go through much trouble. You can search this dataset library on their web by filtering for task category, language, and size. And to load any datasets that you choose, you only need a function from datasets library. So if you decide to use a dataset from Hugging Face, you only need a line of code to load your data. And if you already have your datasets, the loading process is just as easy. Using the Hugging Face datasets library is a smart choice because it is optimized to work with massive datasets. And it has methods that will help you pre-process the data, even if you decide to work with your own data. Once you figure out what dataset to use to fine-tune your model, you need to pre-process the data to feed it to the model for training. The way to pre-process the data varies depending on the task and the model you want to fine-tune. But Hugging Face provides tokenizer objects that ease the process. You only need to specify the model checkpoint you are using, and the tokenizer does almost all the heavy lifting. A tokenizer receives your text data and returns the tokens that your model can read. For instance, you can pass a distill-BERT tokenizer the text with the question, what well-known superheroes were introduced between 1939 and 1941 by Detective Comics? And it would return the numeric token that the distill-BERT model can use for training and inference. You might need to take some additional steps for the pre-processing of your data after getting the tokens that vary depending on the model you want to fine-tune, the dataset you're using, and the task you're training the model for. To ensure that you're doing everything you need to do during the pre-processing step, you need to read the description of your model checkpoint and the datasets you are using, which are also provided by Hugging Face. Now, to perform the fine-tuning of your model, you need to run a training procedure. And as you might already have guessed, Hugging Face will make this step easier for you too. The Hugging Face Transformers library has the trainer object that gets the model that you want to fine-tune as input with some other arguments that you can tweak as needed, such as the number of form-up steps and epochs or the strength of the weight decay. To perform the training procedure, you need to call the training method from the trainer objects, which is just one line of code. Additionally, you can define a function to use some predefined metrics provided by Hugging Face, such as the BLIS score, or even you can define your own metrics if you wish. With Hugging Face, computing the metrics you want with the trainer object is done by just calling an evaluation method on the training, validation, or test data.
Wow, you have covered the encoder and decoder of the transformer network. It is cutting-edge technology, so give yourself a pat on the back for doing this. You will now take what you learned and code it up in this week's assignment. You will implement the code necessary for the BERT model. You will use a pre-trained model for inference and understand how the text-to-text transfer transformers, or T5 model, works. Note that a lot of these latest state-of-the-art models could perform several tasks on the same model just by altering the input. This allows for transfer learning and ends up giving some very good results. Next week, you'll be building a chatbot using the reformer. Good luck in the programming assignment.